right, so sine and cosine, we have talked about. We've used it to solve right triangles, to find angles, to find sides. We've set up the ratios, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. And then we looked at the unit circle, how it gives us the x-coordinate, gives us the cosine of an angle, the y-coordinate gives us the sine of an angle. But now we're going to talk about just sine as an actual function that we can graph, that we can look at its different characteristics and things of that nature. So the sine function is simply y equals the sine of x, okay? Or it could be y equals the sine of theta, okay? It doesn't matter which variable is used there. X and theta are both variables. Typically, we just use a theta with sine and cosine and tangent because theta is the variable that we usually use with angles. But obviously, if we're putting this into our calculator, then we're going to use x instead of theta. So first of all, let's talk about the domain and range. So I want you to go to your y equals, and I want you to type in the sine of x in your y1 before you hit graph. Before you hit graph, I want you to make sure that you're in radian mode. Okay, make sure you're in radian mode, and then I want you to go to your window. I want you to go to your window after you're in radian mode. All right, so in your window, here's what I want us to do. For the x minimum, I want us to do -4 pi. Okay, put -4 pi and then put +4 pi for the x maximum. When you hit enter, it's going to take that pi and convert it to a decimal. For the scale, usually we don't mess with that, but let's go ahead and put pi over 2. I'm just looking at this graph that I'm getting ready to have to put this on, and it's got it marked at increments of pi over 2. For the y minimum and maximum, I'm going to do the same thing that I've got here on my paper, so -2 to +2. All right, so make sure you've got all those settings in your calculator there, and then you can go ahead and hit graph. Okay, so -4 pi to +4 pi for the x min and max. The scale is pi over 2, y minimum -2, y maximum +2. Make sure you're in radian mode. Okay, then hit graph. So you've probably never really seen a graph that looks like this before, unless for at some point in time you have tried to plug sine of x or cosine of x into your calculator to look at it. So first of all, let's talk about domain and range, because you should be able to figure out domain and range for any function when you look at its graph. So when we're looking at domain, the question is, do I see any breaks in my graph? Do I have any holes in my graph? Do I have any jumps or anything like that? And we don't, okay? This is completely continuous. If I put my pencil over here on the left side of my screen, I could trace that entire graph without lifting my pencil. So that means our domain is all real numbers, or remember our interval notation, -infinity to +infinity. That means that we can find the sine of any angle, any number from -infinity to +infinity, any angle, we can find the sine ratio of that angle, okay? How about the range? When you're looking at range, you're looking, is there a minimum value to our graph, something that our graph never goes below, and or is there a maximum value, something that our graph never goes above? Now, we're not looking at the entire graph, but I think that we can see enough of it to see that this is a repeating pattern that's going to continue. It's not going to change. We can make our x min and x max whatever we wanted to, and we're just going to continue to see this pattern repeat. So, is there a minimum to this graph? Yeah. Yes, there is. Okay, we never go below -1. How about a maximum? Yes, we never go above +1. So our range, we can write it either like this: -1 is less than or equal to our y, which is less than or equal to 1, or in interval notation, that would be -1 to 1 with brackets, because we do hit -1, we do hit +1. Okay, we kind of already talked about this, but the next block there says continuous or discontinuous. That has to do with the domain. That has to do with that idea of, do I ever have to pick up my pencil? I don't, so this is continuous. There are no discontinuities. Okay, if it's discontinuous, that means there's some kind of break, there's some kind of jump, there's something going on there. Now, the next one, even, odd, or neither. I think we talked a little bit about even, odd, and neither, but what it means is there's some symmetry going on here. Even functions are symmetric about the y-axis, so the y-axis cuts it in half. So if I folded this graph over the y-axis, would I get the exact same graph on the left side?
No.
Not quite, okay? It's similar, but it's not exactly the same. So it's not even, okay? Odd, its symmetry is a little bit harder to see in terms of symmetry, but the symmetry is that it's about the origin. So that means if you take your calculator, it's easiest to do with somebody right beside you. One of you keep your calculator right side up, one of you flip it over, okay? One of you flip it over so that the screen's at the bottom. Do the graphs look exactly the same? Yes. That is symmetry about the origin. If you rotate your graph 180 degrees, and it looks exactly the same, then that is symmetry about the origin, and that means it's an odd function. We could also look at our table to see whether it's an odd function or not. Odd functions, if you center your graph, or excuse me, center your table between -3 and +3, notice that just we've got some rounding going on, but these are the exact same y values, except they just have opposite signs. So opposite x values, so +3 and -3, have opposite y values, +0.1411 and -0.1411. That's odd. If it was even, they would have the same y values. We'll see that here in a minute. Neither would be if it didn't have either of those symmetries, if it didn't have those opposite y values or the same y values. Okay, so sine is what we consider a odd function. Now, I want to put some points on this graph and fill in this table before we hit these other topics here. So let's adjust our window one more time to exactly what shows up on our graph here. I just wanted you to see a bigger window of it to start with. So this graph goes from -pi to 2pi. -pi to 2pi for your x's, and everything else is going to remain the same because we already fixed the other pieces. I just wanted us to see more of it horizontally to start with. Okay, so from -pi to 2pi, let's look back at the graph. So we should be able really to fill in most of the stuff on the graph here without even going to our table necessarily. Over there at -pi, you can see it is right there on the x-axis. We fixed our scale so that each of those lines on the x-axis there is pi/2. So right here at pi/2, we can see that we're hitting our minimum value of -1. At the origin, we go through the origin at x equals 0, the y equals 0. At pi/2, that first tick mark on the positive side of our axis, we hit the maximum of +1. At pi, we're crossing the x-axis again. At 3pi/2, we're hitting the minimum. And at 2pi on the right side, we're back at the x-axis. Now, I could go through and I could put in a little bit more detail, but since I've got my calculator, I can see what this is looking like. Then I'm just going to connect these points here, making sure don't connect them with straight lines. You're looking at the graph. You can tell they're not connected with straight lines. Put some curve to it there. Okay. Also, based on what I just got, I can fill in that table. At -pi/2, the y value is -1. At 0, the y value is 0. At pi/2, the y value is 1. At pi, the value is 0. So those are just a few select values. Okay, it doesn't tell us everything, but those are just a few select values from our graph. Put them in table form. Now, if you needed to get these and they weren't very clear on the graph, I don't know how many of you know this, you can adjust your table. You can press second window and it says table start. You can put negative pi over 2 there for your table start. And then delta table means, well, how many units is it counting by? Well, this is the same that our graph is counting by. It's counting by pi over 2. So you can change that, and then you can go to your table and you see those values. The only downside to it is it doesn't keep the pi in it. It puts it in decimal form, but as long as you remember what you set it at, you can match those up. And again, notice how those values are repeating. Negative 1, 0, 1, 0, negative 1, 0, 1. It would keep going, okay? Let's see here. So let's talk about the x and the y intercepts next. Okay, the x-intercepts. We have a bunch of them, right? It keeps crossing the x-axis. The first time in our graph that we can see that we have plotted, it crosses at negative pi, it crosses at 0, it crosses at pi, it crosses at 2 pi. So it looks like it's crossing at multiples of pi. So here's how we're going to write that. We're going to write that pi times k. Pi times k. And then, of course, the y-coordinate of any x-intercept is 0. And then down here below our point, we're just going to write where k is an integer. Okay, integers, y'all know, are whole numbers and they're opposites. So when k is 1, pi times 1 is pi. There's that x-intercept. When k is 0, 0 is an integer. Pi times 0 is 0. There's that x-intercept. When when k is negative 2, pi times negative 2 would be negative 2 pi. I know I don't have it on my graph, but again, the pattern's repeating. That would be another x-intercept. Okay, so that's how we include all those x-intercepts with this pattern repeating over and over and over again. The y-intercept, what's our y-intercept? 0, okay, it's the origin. It's right there. 0, 0 is our y-intercept. All right, local maxima. Okay, local maxima. Now it gives the plural of the word maximum. They're not maximums. We call them maxima. Because we have this pattern that's repeating, so we're going to have a bunch of maximum values that we hit here. They're all the same, right? They all have a maximum y value of 1, but they occur at a bunch of different places. Now, the only one that we can see here on our graph is at pi over 2. Okay, pi over 2 is the only one that we can see on our graph, but if we were to zoom out on our graph, we would see that another one would occur at 5 pi over 2. It would also occur at negative 3 pi over 2. So here we're going to add 2 pi k. Okay, pi over 2 plus 2 pi k would give us all of our maximum values. Pi over 2, 5 pi over 2, negative 3 pi over 2. Okay, same thing as the x-intercepts. That would be our maximum. For our minima, we can see 2 on our graph here at 3 pi over 2 and at negative pi over 2. So similar concept here. Let's start with that first positive one. 3 pi over 2 is our first positive one. And we're going to do the same thing. We're going to add 2 pi k to that. And the y value of the minimum is negative 1. The y value of all those minima is negative 1. Now, don't stress out too much over the 2 plus 2 pi k and the pi k for the x-intercept. That's just the mathematical notation that we use to represent all of them. Probably if you're asked a question about it, they're just going to ask you about one in a certain range of values. So it's not going to be something that I'm going to ask you to do on a quiz or on a test there. But you may need to recognize it if it's a multiple choice answer choice. Don't let that throw you off. That's why I want to go ahead and show you that here. All right, intervals of increasing and decreasing. It's been a little while since we've done some of these, but let's look at our graph and look at where this function is increasing. So I see increasing from here to here, right? My y values are increasing as I move from left to right, starting, remember we use the x values. So starting at negative pi over 2 and ending at positive pi over 2. I use parentheses because at negative pi over 2 and at positive pi over 2, that's where it changes. Okay, that's where it changes. That would continue to repeat. Notice it starts increasing again here at 3 pi over 2. And I know that our graph ends, but that would stop at 5 pi over 2. Would be where that interval of increase would end. And then that would keep repeating. Okay, there are more places, obviously, where this function is increasing. We could express it similar to the maximums and minimums, but we'll just leave those two right there that we can see. Okay, intervals of decrease. We can see obviously between pi over 2 and 3 pi over 2, we are decreasing. At the very beginning of our graph, we notice that we are decreasing. That would have started at negative 3 pi over 2, and it ends at negative pi over 2 is another interval of decreasing. And of course, obviously that repeats. We have more to the left and to the right. Now let's talk about one more thing, end behavior. Okay, end behavior. We're talking about, well, what is it doing as we go to the extreme ends of our graph, to the very far left, to the very far right. You don't have to do this on your graph, but really quickly, I'm just going to expand mine even more. I'm going to go negative 8 pi to positive 8 pi, just so we can see a little bit more of the graph. And to re-emphasize, this pattern just keeps repeating, repeating, repeating. So end behavior, we're talking about what are the y values doing on this end and on that end. Are they headed towards one specific value? So that's the question. Are they headed towards one specific value as we go to the end on the right, the end on the left? No, they're not, because this pattern is just repeating over and over and over and over and over again on both ends. So this is something that we call oscillating behavior. So it oscillates. If something oscillates, then that means it's bouncing between, oscillates between -1 and +1. Okay, it just keeps bouncing back and forth between that minimum value that we have and that maximum value that we have of +1. So it never zones in on 0. It doesn't go to infinity. It doesn't have a horizontal asymptote. Remember, those were some of the scenarios that we had where we had an actual end behavior, something that we were headed towards. But in this case, it's not. It's going back and forth. It's oscillating. All right, so most of this is stuff that we've talked about with all of our other different functions. Now, with sine and cosine and tangent, and we're just going to focus on sine and cosine here, we have some new terms, and this is why you have that extra space at the bottom of your page. These are terms that are pretty much exclusive to what we call these sinusoidal functions. Okay? Sinusoidal functions is another expression for these. But we have something called the period or the cycle length. We're talking about the fact that this is a repeating pattern over and over and over again. So the question is, well, how far or what is the distance that it takes to complete one complete cycle of this pattern? So if we look at the graph, let's start at the origin. Okay, we hit our maximum, we hit our minimum, and then we end up back where we started. That took a distance of 2 pi units. So that is what we consider the standard period or cycle length. Okay, remember, all these values that we just talked about here are the standards. When we just have sine of x or sine of theta, we're getting ready to talk here in a second about, well, what if we have some other things going on? Okay, but this is the standard. The standard period or cycle length is 2 pi. The midline, okay, the midline, let me write under this, this is the length of the pattern. Okay, the midline is pretty much what it sounds like. It's a line in the middle of the function. Okay, so if we look at this, is there a horizontal line that kind of splits this function in half? Yeah, what is it? 0. The x-axis, okay, y equals 0 is our standard, excuse me, y equals 0 is our standard midline. Okay, we can talk about that moving, depending on if we add or subtract something else to our function, but y equals 0 is the standard. The amplitude is another term that's new and exclusive to these functions. The amplitude is the distance from the midline to the maximum value, or that could be the minimum value. It's the same distance because these graphs are symmetrical. Okay, the midline cuts it in half. So whether you want to look at it from the midline to the max or from the midline to the min, it's the same distance. Okay, it's the same distance either way. It is always positive. So it doesn't matter if you're looking at going from the midline down to the minimum, we still always consider it to be a positive value. So for this graph, what would be the distance from the midline, right here on the x-axis, to either the maximum or the minimum? 1. Okay, the amplitude, the standard amplitude is positive 1. Standard amplitude is positive 1. Okay, any questions? Okay, let's look at the graph of cosine. Okay, let's look at the graph of cosine. So in your calculator, let's do the cosine of x. Don't reset anything, just go to your y equals and hit cosine instead of sine. I'm gonna leave my window, go ahead and leave your window the way it is. I'm going to leave mine zoomed out and go ahead and graph it. So similar behavior going on here. It's a pattern that's repeating. Okay, it is a pattern that's repeating. We can see that it has the same maximum and minimum values. I am going to go ahead and adjust my window now so that we can graph it the same way that we graphed sine. So let's look at some similarities and differences here. Cosine, I haven't written it down, but obviously cosine x or y equals cosine theta is our cosine function. Okay, domain and range. Any differences there? Any differences from sine for domain and range? No. Okay, still all real numbers. Still between -1 and +1 for the range. Okay, let's go ahead and put our values on here. This time at -pi, we're at -1. At -pi/2, we're crossing the x-axis. At x equals 0, we're equal to 1. At pi/2, we're crossing the x-axis. Pi, we hit -1. 3pi/2, we're hitting the x-axis. And 2 pi, we're hitting the maximum value. So we can draw a graph here. Again, not straight lines. Put some curve to it. And we can fill in our little table here. -pi/2, we're on the x-axis, so we're equal to 0. 0 is 1. Pi is -1. 3pi/2 is 0. So similar to our table for sine, just different locations where we're hitting these values. Okay, so our x-intercepts, still we have a bunch of them. They are repeating, but this time they start at pi over 2, and we're going to add pi times k to give us all of our x-intercepts. Okay, so if k is 1, pi over 2 plus pi is 3 pi over 2. If k is -1, then pi over 2 minus pi is negative pi over 2. Okay, so those are our x-intercepts. So similarities and differences, sine was at pi k. These are happening at pi over 2, multiples of pi over 2. What's our y-intercept? 0, 1, right? 0, 1 is our y-intercept. So we're not going through the origin here. We're hitting our maximum value for our y-intercept. We are, of course, continuous. We don't have any breaks. Our domain's from negative infinity, positive infinity, so we're continuous. Even, odd, or neither. Let's see here. What kind of symmetry do we have on this one? I know we're not looking at a fully symmetric window, but if we folded this graph over across the y-axis, would it be the exact same graph? Yeah. Okay, this one's even. If I go to my table, let's see here, it's a little messed up here, but I think I can get it. Yeah, I can still get it centered up. Okay. Opposite x values, positive 4.712, negative 4.712, have the same y values. Okay, notice I have the same y values for opposite x values. So that is the other way to recognize if it's an even function. Okay, let's see here. Our maximum value happens at 0. It happens at 2 pi. So if we write this in the same way that we did the other, it's 2 pi k. We'll produce all of our maximum values, 2 pi k. So 0, 2 pi, 4 pi, etc. For our minimum, we've got, it's at pi, it's at negative pi. So we have to do pi plus 2 pi k to get our minimum, all of our minimum values. Okay. Pi plus 2 pi k, and the y value is -1. All right, intervals of increase. The first one that I see here is from negative pi to 0. Negative pi to 0. And then it happens again from pi to 2 pi, we are increasing. And again, I could come up with more if I was looking at a wider window. Decreasing, I only see one in this current window that I'm in, and that's from 0 to pi. My function is decreasing from left to right. Again, if I was looking at a bigger window, there would be more intervals of decrease. In behavior, same deal. We're oscillating. Between -1 and 1. It's just at different places where we're hitting those values. Okay. Our period or cycle length looks a little bit different than sine did, but it actually is the same distance. If I look at it, let's start at x equals 0. We start at +1. So we go and we hit our minimum, and we've got to get back to our starting point. We get back to our starting point at 2 pi. So we started at 0, we got to 2 pi. So our period or cycle length here is still 2 pi. Just, it looks a little bit different, but the distance is still the same. Our midline is still the same, y equals 0. Our amplitude is still 1. Okay, the amplitude is still 1. Just again, those maximum and minimum values occur at some different locations, but we're still achieving the same values. Okay, any questions about any of the new vocabulary, any of these characteristics, anything so far? I know I'm talking a little bit more than usual, but I'm almost done. Okay, let's look. This is not on your paper, but flip back over to the sine. Okay, flip back over to the sine side. At the bottom here, I just want you to write this function, f of x is equal to -3 sine of x, -3 sine of x. Now let's just think, we've done transformations of functions. We've talked about, well, what happens if we multiply our function by something, what happens if we add something inside of our function, outside of our function, and whatnot. So who can tell me what this -3 should do to our function here? Okay, I saw somebody say it flips, okay, and it makes it taller. Okay, it flips it and it makes it taller. So let's see if that's indeed what happens. -3 sine of x. Okay, yeah, it doesn't fit anymore. Okay, it doesn't fit anymore. Let me go to my table and get some values here. At 0, I'm still at 0. Okay, let's see here. This would be pi over 2. Now I'm at -3. Okay, so notice the difference. This is what I've got already graphed here is just my standard sine of x function. Okay, that's what I've already got graphed on my picture. So I was at +1. Now I'm at -3 at the same y value. Let's see here. At pi, I'm still at 0. Okay, so my x-intercepts are still at the same place. At 3 pi over 2, now I'm at +3. Okay, I was at -1, now I'm at +3. I can keep going. It gives me a really weird number, but it's supposed to be 0. Remember, that's the scientific notation. When you see that big of a number following that capital E, it's scientific notation. Then I'm back at -3. Then I'm back at 0. Okay, so I keep the same shape. I've just flipped it over and made it taller. Okay, that's all that's happened here. I'm not doing a very good job of drawing, but you get the idea. Okay. So let's talk about those three things. Okay, let's talk about period, midline, and amplitude. What changed? What didn't change? Okay. Did the period change? No. Okay, the period did not change. I still have my complete cycle by the time I get to 2 pi. So the period did not change. Did my midline change? No. Nope. Still at y equals 0. I didn't move up and down. That's still right in the middle of my graph. How about my amplitude? Yes, it did change. Now to get from my midline to my minimum or my midline to my maximum, it's 3 units as opposed to the 1. Okay, so this constant right here, we call it A, and that works nicely because that affects our amplitude. Okay, so whatever that number is, that is the new amplitude. Now, again, it's always positive, so the negative here just flipped it over. My amplitude is +3. The negative just flipped the graph over. Okay. All right, let's see what happens here. Sine of 3 over 4x. The sine of 3 over 4x. Think back to our translations. What happens when we multiply the x by a number, or inside of our function we are multiplying by a number? When it's with the x, is it a horizontal change or a vertical change? Horizontal. Okay, all of our horizontal changes, were they what we expect them to be, or were they the opposite of what we expected them to be? The opposite. So if I multiply by 3 over 4, what are we expecting?
It to get smaller, but it's really going to get bigger.
Yes. Okay, 3 over 4, we would expect that to get smaller because it's less than 1, but it is actually going to expand this horizontally. So I'm going to type this in so we can see. Okay. If I keep my window the exact same as what's on the paper, I can't even see a complete cycle. Okay, I can't even see a complete cycle anymore. So what it has done is it has expanded this horizontally. So let's go through and talk about what it's changed. Period, midline, amplitude. Let's talk about, first of all, what it has not changed. Okay, it has not changed our midline. It has not changed our amplitude. We haven't done anything to those. Okay, so our midline for this one is still y equals 0. The amplitude's back to the standard of 1. It has changed our period because I can't even see a complete cycle right here. Now, it's harder to see this on the graph and figure it out from the graph, so that's why I want to explain it from this perspective. This is the coefficient that we call B, and it always affects our period. So the new period, here's how you find it. It is 2 pi, it's always your standard, divided by that B. Okay, it is 2 pi divided by that B. So let's do that here. 2 pi divided by 3/4. What do we do when we divide by a fraction? Multiply by the reciprocal. So 2 pi divided by 3/4 is really 2 pi times 4/3. And so that's 8 pi over 3 is our new period. 8 pi over 3 is our new period. 8 over 3 is somewhere between 5 pi over 2 and 3 pi. Okay, so it'd take us that long to complete that entire period. Now, it does still stay symmetrical, so halfway through that, we would hit our minimum. So I can kind of sketch out, I can break this up into quarters and kind of, I didn't do that very good. That one should be over a little bit more. Okay, I can still sketch what should happen. That one's over too far. No. Oh my goodness. No, I was in the right spot. That is where that should be. There we go. One complete cycle. This middle should probably be over a little bit more. Okay, but one complete cycle from 0 to 8 pi over 3. Stretched it out there. Okay, I was getting distracted by the rest of the graph. Okay, almost finished. Let's talk about the last one. We've changed the amplitude. We've changed the period. What's left? The midline. Okay, the midline is left to change. So sine of x plus 2.5. So there are no parentheses right here, so that means that plus 2.5 is outside of the trig function. Okay, so there are no parentheses in the problem, but when you type it into your calculator to look at it, it automatically starts the parentheses, so you have to make sure that you close them after the x. Okay, you have to close them after the x. So sine of x plus 2.5 here. Let's look at the graph. I can't even hardly see it because it has moved this up 2.5 units. So we have not changed the period because we didn't multiply the x by anything, so it's still 2 pi. The midline is what has been changed. So remember, if we add or subtract something from the end, it shifts it up or down that many units. So we were at 0, now we're at 2.5. Our amplitude, though, we didn't multiply our sine function by anything, so our amplitude is still 1. So if I was going to sketch this out really quickly, I would just put this up here. Everything just moves up 2.5 units. Okay, it occurs at the same place. It's just 2.5 units higher than it was before. Okay, makes sense? Okay. So, last example, here's a cosine. Let's put a little bit of everything changed on here. Okay, let's put a little bit of everything here. I use the theta this time instead of x, just again to re-emphasize the fact that it doesn't matter whether it's theta or x, it's still a variable. You can use either one. So 2 is our A, 4 is our B. I didn't tell you what that last one is, but we call it D. There is another letter. Obviously, we skipped C. We're not going to talk about that one in this class, so you don't have to worry about it. So the midline change is the constant D. So A affects our amplitude. The amplitude of this function would be 2. B affects our period, so 2 pi divided by that number in front of the x or the theta, so 2 pi over 4. That reduces to pi over 2. So instead of completing one cycle between 0 and 2 pi, now we're completing it between 0 and pi over 2. So we have squished this pretty considerably, which makes sense, remember, because when that number is bigger than 1, we would expect it to make it bigger, but it actually makes it smaller. And our midline, we have subtracted 3, so our midline is going to be at y equals negative 3. So we have squished it, we have moved it down, and we've made it taller. We've squished it horizontally, and we've made it taller vertically. So you got to be able to recognize these 3 characteristics from the equation. You really shouldn't even have to look at the graph because I think a lot of times some of those are hard to see on the graph, particularly the period is hard to see on the graph. But those characteristics that we talked about at the very beginning, those are characteristics that you should be able to determine about any function, sine, cosine, exponential, square root, anything like that, you should be able to find these characteristics of.